All right, let's get underway. So it's Sunday evening, long day, long weekend. Um, this is from probably a week or so ago, and we had some snow, and it was bitterly cold. And so Dora is wearing a fleece and her coat, but she loved it, and there were still squirrels. Frog Pond is her favorite place because there's just so many squirrels. That's what she lives for. I think she just dreams about them all night long. So let's get started. So, test two. Test two, I knew it wasn't going to be grades as good as test one, but they're still lower. And this class, a lot lower. Um, that I'm still wading through what people had trouble with in the different classes. Excuse me. Um, I think generally a lot of trouble with the pivot table ones. This class had trouble with a whole bunch of others as well. So I've got to dig through this further as to how we're going to adjust grades. And I probably mentioned at the beginning of the term, um, I do adjust grades on a regular basis with tests upwards only, not downwards. The uh, there's over 400 students taking the course, and so with that many students, if the overall grade is low, it's not the student's fault. It's not a good class or a bad class. There's many different variation in grades. It's the test itself. And so normally I do make adjustments. And I don't generally scale by looking at a percentage change. Uh, if there are issues with specific questions, I may allow, if the right answer was C, I may allow answer B because it was almost right. But more often than not, I just move everybody up by the same number of points. And so everybody gets the same benefit of any adjustment. It's anyway, the um, but I'll get back to you more. I'll probably email folks because a lot of you don't see the videos. So Tuesday, because we have an assignment that's due on Friday, I'll be doing a tutorial and I'll do it at 1 on Zoom and have it recorded. Most people don't show to my tutorials, and last time we ran into problems and uh, I had to do it later anyway. But the last one had about 700 views. As I said, we've got over 400 students. So I guess some people viewed it more than once. Uh, but that's been what students have done in the past as well. So, but like I told you on assignment one, if you're watching this, please, or you're, mm, uh, try the questions, do as many as you can before the tutorial or before you watch the recording. And if you're watching the recording, only play it for questions you've already tried. As soon as you hit stuff that's new, I'd like you to try it and then you watch the recording. Okay? Wednesday's discussion, it's about why my favorite foods are bad for me. And uh, that I've asked this one to classes before. Invariably, something comes up in the news just before that reminds me of this. And most recently, it's the debate about alcohol consumption, that they're now saying that the maximum per week should be no more than 2 drinks. It used to be 10 for women, 15 for men. So that's a big change. And so, how do they do the research to be able to do that? Think about it. How do you do research on diet? It's really, really hard to do. And it's we can't do experiments generally. They're generally observational studies. And when that happens, we get what we call confounding variables. Now, we just looked at Simpson's paradox last week. That's the case of a confounding variable, some hidden variable or one that we're not focusing on that causes. So if you see when A happens, B happens, is it A causes B to happen? No, it could be some confounding variable C that causes both A and B to occur. So it's more complicated than that. And dietary research is probably one of the hardest areas to do very good quality research in. So Friday, that assignment is due. Saturday, we've got a quiz. Not quite though, because we're going on break. So I think in the course outline, I said it was due Saturday. I moved it to the 25th. So that's the Saturday at the end of the break. But I'll bet you there'll be more people forgetting the quiz this time than any previous quiz. Because if you don't do it this weekend, you're going to forget about it altogether. Anyway, off we go. A few things happening in my in-person class. They've been asking regularly about the strike. So the union has got a town hall on Wednesday that to try to answer questions about the strike. This is my 44th year at St. Mary's, and we've never had a strike since I've been here, and they never had a strike before I was here. So this would be a first if we do walk out. But I think the faculty are in a mood that if they don't see some change, then they are quite prepared to walk out. That I know break is coming up, but on Saturday is the 27th International Night. I'm sure we've had more than 27. It's been such a regular occurrence for so long, but I've actually never attended one, but I always heard that it was an amazingly good event. I'd encourage you to take a look. So here we are, we're into day 11. We're transitioning now officially into modeling, which is, we had business understanding, data preparation, the data modeling. And modeling is generally seen as the fun stuff. It's the math stuff. Whereas everything before is just summarizing things, cleaning stuff up. And in many courses on analyzing data, all they focus on is the modeling phase and not all of the grunt work that comes before it. In most projects, 70 or 80% is in all of that work that leads up to modeling. So we're going to continue with the same setting we had last class, where we're looking at a data set that is supposed to be customer credit card records and looking to see, can we predict their credit card balance based upon customer characteristics. So we've got records for 400 customers. We've got the balance owing. That's, we call our target variable, what we want to predict. And we've got a number of, I'd call predictor variables or explanatory variables. Things like their income, credit rating, credit limit, age, education, number of credit cards, gender, marital status, student status, and ethnicity. Again, why do we want to do this? Very often predictive models are not actually to do a prediction per se, but indirectly that's what's going on. So if you are looking to see if financial activity was unusual, you would have a model that would predict what should you be seeing, and then you'd look at what you actually saw. And if you find that those two are very different, it's worth looking into. It may not be criminal, but something strange is happening. Maybe my credit card balance will skyrocket if I go out on strike and I don't have a regular paycheck. I'm living off my credit card. Sometimes it's just trying to understand borrowing behavior, that why do people borrow as much as they do? And if we want to encourage them to borrow more, are there levers we've got to encourage that behavior to change? Or sometimes it's indirectly to do classification. Can we come up with a model that will flag for us who are the ones that borrow a lot? And from there, so that's like a classification. And I want to know the big borrowers because maybe I want to sell them insurance in case they lose their job, and who's going to pay off their balance, or if they have an accident and go off on disability. So there's I'm trying to cross-sell on other financial products I'm trying to sell them. So what variables give us insight about credit card balances? We looked at scatter plots, and we saw that 3 of them seemed to have a bit of a pattern and 3 of them didn't seem to have any pattern. So, but these things aren't models. We're trying to explain things. We'd like to have some integrated piece that we'll call a model that pulls all that stuff together. Now, we're going to be looking at mathematical ones for the most part, but also in practice, we sometimes build physical models, a mock-up of what something will look like, and maybe how it will function. We've got verbal models of things. This leads to this, leads to this, maybe a model. Some are in pictures. Some of the verbal ones we show in pictures. Sometimes it's a drawing. It's a sketch of if I have blueprints for a house, that's a model of what the house will do. What are the different, how the different rooms interact with each other. They're never exact. They're just approximations. They only show certain elements of what's happening there. But of the features that we think are important, we'd like to have an accurate representation of what they are. So beginning of the course talked about different types of models. There were descriptive models, profiling, just getting a description of what does that serial killer look like. Co-occurrence grouping, people that bought this also bought this. That's a model in a sense of a describing shopping behavior. Clustering, trying to take all your customers and group them into clusters so that those within a cluster are similar to each other in many different ways. But if I look at 2 different clusters, they look different. Sometimes I'm just trying to match similarities between individuals, and sometimes I'm trying to explain what's going on. So these are descriptive things. I'm not making a prediction of the future. That they just describe what's happening. And in machine learning, they call it unsupervised learning. You're not controlling, in a sense, the learning process. On the other hand, there's ones that are supervised learning. Those are predictive models. We've got a target in mind that we're trying to predict. Is this customer pregnant or not? When's the baby due? That the biggest ones are value estimation, predicting a number, and classification, predicting a category. That is this, are they going to default on the loan or not default on the loan? Is this a good customer or a bad customer? Is this transaction valid or fraudulent? That's a lot of classification ones, and also a significant number of ones with value estimation, predicting a single number. These are link prediction, yeah, that LinkedIn tries to predict, do you know this person or have you thought of joining up with them? Trying to predict who you should form relationships with. That generally what they're doing is we've got historical data on, say, on customers, and in the case we're looking at is historical data on their credit card balances. And so we've got a target, that was credit card balance, that we're trying to predict based upon the other data that we've got. And we train the model by trying to build a model, and if it's making good predictions, we say, yes, do more like that. And if it's making bad ones, we say, no, it's not working, make it better. It is training, just like you're being trained to do certain tasks, like a coach trains you if you're an athlete, that type of thing. It's supervised. Now, just to remind you, why do we need models and where do these things come up? Even if you're looking at basic marketing has a whole bunch of stages to it. It's not just advertising. That you've got prospects out there, that potential customers. You've got to find a way of defining who they are, profiling who they are, finding them. that if you found them, you put something out to them and see if they're going to respond. So you're building models to see what are things they are most likely to respond to and what things wouldn't they respond to. That if they do respond, you're trying to convince them to become a customer and get over to that stage. And if you're lucky, they become a new customer. They buy something from you. That whole acquisition phase is huge. That once you've activated them as a customer, you want them to come back and buy more. And so you've created a relationship with them and you work with that established customer in terms of getting them to come back over and over again. And so it's a different phase of your marketing process. And along the way, you lose some. They just stop buying, or it was a cell phone customer and they don't renew their plan with you, or an internet customer and they don't renew their plan with you again. And you don't just leave them there, that you'll get into another phase of trying to find ways of taking a former customer and bringing them back into a regular customer again. And there's a whole bunch of data mining questions and models you may have. Some are predictive, some are descriptive. That defining the profile of a good customer, you've got to figure out how do you measure how good a prospect is. So you've got many customers out there, but who are the really good ones and who are the so-so good ones? That what channel should you use to reach that prospect? Channel being communication channel you're going to use. Then even if you know, like, it's maybe what website you're going to advertise on, but then what's the message on that website? That, again, which ones will you are trying to predict their response on different channels and find what's the best channel to use to get the response that you want. That you're going to be looking, even if they respond to things, what's the chance I can convert them into a whole new customer? Or what's the payoff? Some customers, there's a big cut payoff too, and some small amount. So I may be doing value estimation to predict how much I should be able to generate as income from this particular customer. And if it looks like, hey, this is a lot of income, then it's one I'll go pursue more aggressively than someone that I think the income is going to be lower. You can imagine a whole bunch of different types of models that we've got. So within a single business problem, generally we've got a whole bunch of models we might want, and of different types. Okay, that not going to go through all of them. We're going to focus on value estimation models, so predicting a number. And we just saw scatter diagrams that showing credit rating or income, what have you, what's their value in predicting the credit card balance. And we had even a correlation coefficient to tell us which ones seem to be better predictors than others. So things have positive or negative correlations, but generally we're most interested in how strong that relationship is. So we had a bunch of these things. These were all positive, but we'll be equally interested in negative ones. And the closer it is to -1, probably the more important that variable is. But remember, those are only straight line relationships that we get with correlation coefficients. We're going to be paying a lot of attention to straight lines, to linear relationships. But we have to be careful. You'll find even with very high correlations, here's one here between credit limit and their balance, looks like a very, very strong pattern, but there's still a lot of scatter. Look how the difference between high and low from $500 to $1,500. So there can be a lot of noise even with a very high correlation. So if we're trying to go and build this as a formula, and that's where we're going to start, and that normally when building a formula, it's recommended, I recommend anyway, others may differ, start off simple. that complexity comes at a cost generally, and cost in a broad sense. That there's, you may have heard of Occam's razor. I don't know who Occam was. And it's a strange proposition or thing called Occam's razor. What's a razor? You know, I shave with a razor. Anyway, it's called Occam's razor. And it's advice on when you've got choices as to how to solve a problem, that generally the simplest solution is most often the best one. So start simple. So if I'm building a formula, what's the simplest type of formula you can get? Simplest relationship between an x and a y? It's a straight line. And it only has one variable. So one x variable predicting one y variable. That and I'm going to, my y variable, I'm going to call my target variable, and my x variable I'm going to call my predictor variable or explanatory variable. We're going to look at straight lines. You've seen straight lines. If you did Quant 1, you saw a lot of them. You've probably seen them all through junior high and high school. But surprisingly, a lot of people still don't quite understand what their straight line is telling them. So let's go and use a very simple cost function. It's got a fixed cost, say $5,000 to start up, a startup cost. It's fixed in the sense that no matter how many units you make, you're still stuck with the cost of $5,000. You make 1 unit or 1,000,000 units, you still have to start out spending $5,000. And it's for equipment, insurance, facilities, things that you have to be able to get started. And then once you start making, well, then we're going to have labor and materials and energy and a whole bunch of other things. And the more units you make, the more that variable cost will accumulate, or the total variable cost. So we're going to keep it as simple as possible with a straight line by saying each additional unit we make costs $4. So if I was making the first one, it's going to cost me $4. If I'd already made 1,000 and I wanted to make one more, it'll cost me $4. So each additional unit after I've committed the $5,000 costs me $4. So there's my cost function. Total cost is 5,000 plus $4 times number of units. Simple, but think about that. It's really important. So total cost is some will call it a dependent variable. Total cost depends on the other variables. Very often in data mining, they call it a target variable. X is, statisticians will often call it an independent variable, opposite of dependent. Some will call it an explanatory variable. I like to call it a predictor variable. Some data miners call it a feature. Confusing. And the numbers again, the 5,000 is known as the intercept. It's the starting value. It's what's the cost when x is equal to 0. So if I had my formula back here, if I had 0 in there for number of units, I'm going to get 0 times 4 plus 5,000. So 5,000 is the cost when I'm making nothing at all. And $4 is the slope. So it's the increase in cost when you make one more unit. And the slope is constant. It's a straight line. With a curve, the slope changes on you. Sometimes it's steep, sometimes it's flat. We're not going to deal with them. We're going to have a constant slope. Every additional unit is $4. And so we'd say there's no learning effects taking place. Usually when you're making products, the first few are very expensive to make. You make a lot of mistakes, you're learning, you get better at it. Then after you've made an awful lot, you get really good and quick at making them, and your costs get smaller. We're not going to assume that. We're going to assume it's $4 all the time. Okay. So if this is what I'm doing, I'm trying to predict balance. That's my target. I need to pick a variable for X that is going to help me make good predictions of balance. And if we look back to our correlation coefficients, which are linear correlations, the strength of a linear, a straight line relationship, rating had the highest correlation. So using rating will give us the best straight line because it is the one with the strongest straight line relationship. That's where we'll begin. So there's my scatter diagram, and I'm going to put a straight line through that. And I'll probably draw it through the middle of the scatter. But we've already seen that you can define middle different ways. That what's the best line to draw through there? Which line would give the best predictions? Well, there you're going to have to define best for me. What is the best prediction? And if I'm trying to predict balance, if I predicted the balance to be $1,000 and the balance turned out to be $985, I'd say my prediction was quite good. I was only off by $15. But if I predicted 1,000 and the actual balance turned out to be $2,000, then I'm way off. That's a really bad prediction. It's a big error in my prediction. I would like to be able to draw a line so that my errors are as small as possible. Smallest prediction errors. Now, some of my predictions will be good, some will be bad, so I'll probably look at average. All right. What does that look like? Oops, excuse me. There we go. So this isn't that data. This is just some stuff I made up. And here are a bunch of dots, little blue dots. And the vertical line that you see here is the gap between the point and the line. Now I'm measuring it up and down because I'm trying to predict the value of y for a given x. So I've got an x value here. I'm trying to go up and predict y, go across that way. So if this was my prediction, it's up here, and the actual was way down here, I've got a big error. But I'm looking up and down. I'm not measuring the distance from the point to the line going in a diagonal. I'm not measuring it horizontally. It's up and down. Right? But I've got to ask myself, are all those errors the same? Like these little ones here, do I even care about them? I know I'm going to make mistakes, but small ones I don't care about. I'm really worried about this big one here, this big one up here, this big one here. Those ones are troublesome. And so how bad are they? That if you were off by $1 or $10, when you're off by $10, is that $10 10 times as bad? That if I poke you with a little knife and I just tap you a little bit, you make a little, you might bleed a little bit, might break your skin. And if someone went and poked you many, 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 many times, you'd get maybe a little, okay, put a little Band-Aid on, put a little Band-Aid on. I can handle that. But if someone took me and sliced me with a big knife, that may be the equivalent of 100 little pinpricks, but I might die, whereas little pinpricks didn't matter. So that big slice isn't 100 times worse. It's a million times worse because they're all of the cuts are together. Often small errors are not a big deal, but big errors are really big. They could make you go bankrupt. So it's not generally just a simple, steady the error gets bigger, the cost to me gets bigger in a straight line like this blue line. It's often like the orange curved one, where I really don't care about little ones. No big deal. But when it gets big, the cost to me gets really, really serious. So we're going to be going and looking at cases where it's a curve type cost function. Don't ask me what the right curve is. I don't know. I just know that I want to put bigger penalties on big errors, really big penalties on them compared to small ones. So what we're going to do is look at squaring the error, because mathematicians like squares. That, like we'd seen before with measuring variability, they didn't like looking at absolute difference between the prediction and the actual, or X, and what the average is. They looked at not simple absolute deviations, but squared the deviations. That's what we're going to do here. We're going to look at squared deviations between what the prediction was and what actually happened. So it does have the right idea of assigning a bigger penalty. Why should it be squared? Why not to the power, 3.2 or some strange thing like that? The math gets nice if we square it. And we don't know what else to do. So what we're going to do is minimize the average squared error, the mean squared error. So that's what it's called, mean squared error. And so you find a line, find the prediction, subtract what the actual was for each of the points. What's the gap between each of the points in your line? Square all those things, add them all up, average them out, and then keep doing that and search to find the best line that minimizes that. And estimating that best line is known as ordinary least squares. Ordinary? And it's because there are other types of methods that involve least squares where they do other things. But the simplest one, and we're keeping things simple, is called ordinary least squares. It's the most common approach that's used for fitting a line to a bunch of points. So my ideal line, my actual model balance, has some fixed component, something related to your credit rating, okay? And then there's noise, because the points don't fall on the line. They're scattered above and below, okay? So my intercept is what your balance would be if you had a 0 credit rating. That doesn't make sense, but we'll get to that. And the slope, beta 1, these are Greek letters here, and that's the true values we often use Greek letters for, is how much your balance will go up as your credit rating goes up. That we can't estimate what the noise is. We can only try to estimate what the line is. And our estimate is often written as a Y with a little hat on the top, little pointy thing on the top, like a roof. And this reflects our estimated balance, because we can't calculate the true balance. And the slope and intercept values that we calculate from our sample are only estimates. So if I took another 400 customers, did the same type of thing to try to find the slope and intercept, I'll get slightly different numbers because it's a different sample. So I use these symbols B0, B1 to reflect my estimates of the true values, beta 0, beta 1, which I wouldn't know unless I had every customer imaginable in the past and in the future to be able to go and estimate the line, okay? So I've got a true line out there, and that I'm going to get an estimated line. That finding that line, I can give you formulas for doing it. It's based upon calculus of minimizing those square differences. And it turns out they're nice compact formulas to be able to do the calculations, but they're still tedious to work with, a lot of work. And we'll let Excel do all of that work. But nobody does it by hand. But remember, we're only going to estimate the line, the true line that goes through. We won't estimate actual balances. So like here might be my estimated line, that red one, but there's scatter above and below it, because the actual amount sometimes higher than my estimate, sometimes lower. Okay, we're only estimating the red line. On average, how much do people with a credit rating of 400 borrow? That would be the red. But some customers will borrow less, and some customers will borrow more, even though they have the same credit rating. So I'm looking at this estimated line here. There's a true relationship that sometimes people say that we're going to try to estimate the signal, and that's this formula portion here, separate from the noise. And some people talk of signal and noise. Noise I can't estimate, but I can estimate the signal. And we're going to use it using a technique that ordinary least squares. Most people call it simple linear regression. Finding a line through a scatter, many people will just call regression. And this one is linear, we're estimating a straight line, and we're doing the simplest model you can, only one x variable. So it's often called simple linear regression. And remember, it's the best line through the data, best in the sense that the squared distance from the line to each point up and down is minimized. That square distance is minimized. And it tends to penalize values that are far above or far below will have a big influence on the line. They'll pull the line up or pull it down. That whereas the ones close to the line have very little impact at all. Okay. And we'll use Excel to do all the hard work for us. So I'm only giving you the theory, if you like it, today. And next class, we'll go and show you what it looked like using Excel. And then actually the hard part comes. It's not getting Excel to give it to us is easy. But now I get the output back from it. And I get an estimated slope and estimated intercept. What do those numbers mean? Can you interpret them? Could you explain them to somebody else? That we've got scatter above and below the line. So they'll be saying, well, how accurate is your prediction? How do you measure accuracy? That it's going to end up being sort of like measuring variability. How do you measure that type of thing? If you're asked, okay, I've predicted that this customer should have a balance of $1,200, but their actual balance could be higher or lower. That's my estimate really of the average balance of all customers with a credit rating of 600, I think, borrow $1,200. But individual customers, that's making an individual prediction. How accurate will your predictions be? That's something we're going to want to look at. We're also going to look at two terms one called R-square and the other one standard error, something that we looked at previously. Those turn out to be incredibly important terms, and the standard error is often misunderstood. And R-square, for that matter, is often misunderstood, but we'll leave that to next class. And that is the end. Okay, you guys take care, and